All right, hi everyone. So this is the solution video for the April 3 worksheet. And the first question is this whole big set of molecules, and you're asked to identify the nucleophile, which is another word for Lewis base or electron donor, and the electrophile, which is another word for Lewis acid or electron acceptor. So the nucleophiles are maybe in some case a little bit easier, because pretty much anything that has a lone pair of electrons or a negative charge can use those electrons to form a bond. Now that doesn't mean it's going to, it means it could. So for example, this chlorine has 3 lone pairs. That could form a bond to something else. Most often chlorine is not going to do that, but it could, and that's the key here. So this chlorine is a nucleophile, and I'm just going to abbreviate that NUC. This oxygen, with its lone pairs, is a nucleophile. This anion, this methoxide, that is a nucleophile. Okay? This one, a cation, no lone pairs anywhere, no negative charges anywhere, all of the electrons are in bonds, so there is actually no nucleophile in this cation. Okay, none at all. And in this one, the pi bond, it doesn't have to be there to hold the molecule together. One bond needs to be there to hold those 2 carbons together, but the second bond, or pi bond, does not. So this pi bond, you could actually use those electrons in the pi bond to form a bond to something else rather than to hold those 2 carbons together. Okay, so there they are in these 4, and again, this one does not have any because there's no lone pairs and no negative charge. With respect to electrophiles, well, anything that's a cation means it's missing electrons. So that's a very obvious one, right? So this cation is an electrophile. Here, again, there's nothing. There's no polar bonds, there's no cations, there's nothing in this that would sort of, so this one now has no electrophile, okay? This one, well, this C double bond O, we know from earlier on, is a very polar bond, right? With the carbon being much less electronegative than the oxygen. So it turns out this carbon of the carbonyl is an electrophile. It can accept electrons from something else. That's a nucleophile. So again, this polar bond, the carbon, is the electrophile. Here also, carbon-chlorine is a quite polar bond as well. Again, with the carbon being the delta plus, right? The chlorine is more electronegative. So this carbon is also an electrophile. And then this one, again, this is an anion, so that's a very good nucleophile, but technically this bond here is also quite polar, this C single bond O. So this carbon could also be an electrophile. Again, it really doesn't act that way too much because this oxygen is so strong, but it could. Okay? So there's some nucleophiles and electrophiles. So let me erase that for a second and then start to get the reactions up here for question number 2. Okay, and in number 2, we're actually going to now start to draw what are called mechanisms, that is showing how the reactions occur. And I just need to pull this sheet up here so I can actually see them. So give me just 1 second here. Okay, here we go. So what we need to do is draw the arrows to show. So the full reaction is there. So what we have is the anion from an alkyne reacting with an alkyl halide. And I've given you the products for these reactions. The product is Br minus and this compound. Okay? So we've actually formed a bond between the carbon and this one, and the Br minus has left. Well, we know this anion is going to be a nucleophile. And we know this carbon-bromine bond, again, is quite polar, right? So delta minus here and delta plus here. So this carbon here is the electrophile. So those two things are going to react with each other. This has the pair of electrons, this is missing them. So this is going to come here, and then Br minus is going to leave. And maybe I'll actually get a different color for that. Let me erase those two arrows and try it with a different color here. Okay, just to maybe make it a little more clear, so that we don't get confused between all of these different things. So again, this has the electrons, that's the nucleophile. It forms a bond to the carbon here, which is the electrophile. And then this carbon-bromine bond becomes a lone pair on that Br, so that there are now 4 lone pairs, and that's Br minus. Okay, so there's the first one. Okay, the second one is a little bit different. It's a single molecule with a charge in it. Okay, so this one happens to be, there's that minus charge, there's an OH here, and there's an OCH3 there. And this breaks apart or falls apart, decomposes into 2 products. A carboxylic acid and OCH3 minus. Okay, so if we look what we have here, this O minus, that has electrons it wants to use to form a bond to something. So that, oops, sorry, wrong one. So that is going to be the nucleophile. Now we need to think about, where do those electrons end up? Where do those electrons end up? Well, we're taking a pair of these and forming a bond to this carbon. So that carbon turns out to be the electrophile. And if you think about that, look at this carbon. It's bonded to 3 different oxygens. All 3 of those oxygens are pulling away. So this is very strongly delta plus, right? That's delta minus, that's delta minus, and that's delta minus. Okay, so now what's going to happen? One of these lone pairs is going to make our C double bond O, but we know carbon cannot have 5 bonds, so this bond is going to break and become a lone pair on that oxygen. So we freed this OCH3, that bond is now one of these lone pairs, and we have now reformed, right, the double bond between the carbonyl there. Okay, so that's the second one, so that's 2 of them. So here we had 2 separate molecules reacting, here we only had 1. And then there's a couple more at the top of the second page. So I'll do those here quickly as well. Okay, let me just scroll down here a little bit so I can see them. Yeah, here's one where we have an alkene. Okay, so we've got a C double bond C. And this is reacting with HCl, which we know is a strong Bronsted acid, but it's also a strong Lewis acid. So we're going to get Cl minus, and we're going to get this cation here. Okay, well, we know this one again is a very polar bond, right? And we know HCl is a very strong acid, both in the Bronsted sense and Lewis sense. So this H of this HCl is going to be the electrophile, or Lewis acid. Here again, this pi bond, and we saw that up above, is going to be the nucleophile. So the pi bond has the electrons, the hydrogen does not. So we're going to use a pair of electrons to form a bond to the H. And then this Cl is going to again leave. We're going to break that and make that a lone pair on the chlorine. So this chlorine now is Cl minus with 4 lone pairs, and we formed the bond between this C and that H, and then that leaves the carbon on the left-hand side short a bond. So that's now a carbocation, or positive charge. Last but not least, this is sort of the opposite of one we did earlier. So here we're going to have an ester, OCH3, and we have OH minus, hydroxide. Okay, and what we're going to get out of that now again is a single compound. That looks like this. Okay, so again, anytime anions are there, that's going to be a good sign that it's a nucleophile. So this OH minus is a nucleophile. And once again, this carbon of the C double bond O has all of those oxygens pulling electrons away from it, right? So that, by virtue of being part of such polar bonds, is going to be our electrophile. Okay? So if we think about what happens, a pair of electrons from this OH is going to be used to form a bond to that carbon, and we're going to break this C double bond O and make a lone pair. So one of these lone pairs used to be this bond, and we have formed a bond now between the O and the carbon of the C double bond O. Now again, this is electrons. In this case, we happen to be transferring an H, right? But in all of the other ones, we were simply forming different bonds. There were no H transfers in any of those other ones. Okay, so we'll continue on with nucleophiles and electrophiles Monday as well.